Welcome back to Hansen Theory. So far, you have learned about molecular forces, Hansen space, Ra distance, and red number. You understand how solvents and small molecules interact. But coatings are not just solvents. Coatings are polymers. And polymers behave differently. This episode is where many engineers hit a mental wall. Polymers are not small, simple molecules. They are long chains, flexible, entangled, and often functionalized. They do not dissolve the way dyes dissolve in water. They swell, entangle, partially dissolve, and respond differently to different interaction forces. Understanding polymers is essential because no solvent system will behave the same way with every polymer. No solubility sphere is perfect. No red number guarantees success. Polymers introduce size, shape, and conformational complexity into Hansen theory. Let's start with the first insight. Size matters. Long polymer chains have multiple repeating units. Each unit has its own interaction potential. Dispersion, polar, and hydrogen bonding forces accumulate over the chain. This accumulation amplifies interaction energy compared to small molecules. A polymer may tolerate a solvent that works perfectly for a monomer, but fail with a higher molecular weight version. This is why high molecular weight acrylics dissolve slower than low molecular weight ones. This is why viscosity changes dramatically with chain length. And this is why using solvent recommendations without considering polymer properties is risky. The second insight is about functional groups. Polymers often contain polar groups, hydroxyls, amides, or carboxyls. These groups interact with solvent molecules through polar forces and hydrogen bonding. Even if the polymer is mostly nonpolar backbone, functional groups create pockets of strong interaction. These pockets define local solubility behavior. They can cause uneven swelling. They can create partial solubility zones. They can lead to haze, gel formation, or pigment flocculation. Now let's discuss swelling. Polymers often do not fully dissolve. They swell. Solvent penetrates the polymer matrix. Chains expand. Interaction forces balance the solvent inside the polymer network. This is where Ra distance and red number guide your choice. A solvent outside the polymer's solubility sphere will not penetrate enough. Swelling is incomplete. Compatibility is poor. Process and performance suffer. Next, consider co-solvent effects. Polymers respond differently to blends than to single solvents. One solvent may dissolve part of the polymer. Another solvent may balance hydrogen bonding. Together, they move the system closer to the center of the solubility sphere. Experienced formulators treat polymer behavior as a multidimensional optimization problem. They do not select one solvent. They design a combination that balances interaction forces. Now, let's explore polymer-polymer interactions. Many coatings involve more than one polymer. Blends, copolymers, and additives are common. Even when each polymer is compatible with a solvent, they may not be compatible with each other. Hansen theory helps visualize these interactions by placing polymers and solvents in the same space. Distance between polymers in Hansen space predicts miscibility. Too far apart, and you see phase separation. Close enough, and you achieve a stable blend. Now consider additives. Dispersants, surfactants, rheology modifiers, and crosslinkers introduce additional interaction points. They can enhance compatibility, mask polarity mismatches, or disrupt hydrogen bonding. But they can also destabilize a formulation if not properly matched. Here is a key mindset lesson. Polymers magnify molecular forces. They expose weaknesses in solvent selection. They reveal the limits of single-parameter thinking. They force engineers to apply Hansen theory in its full depth. Understanding polymers through Hansen theory is not optional. It is essential for anyone working with high-performance coatings. Now, let's connect this to production. Polymers react to environmental conditions. Temperature, shear, humidity, and concentration affect swelling and solubility. During mixing, solvent penetration changes viscosity. During storage, partial solubility can cause settling. During application, solvent evaporation can shift polymer-solvent balance. Engineers who ignore polymer complexity rely on luck. Engineers who understand polymer behavior predict problems and control outcomes. The takeaway is simple but powerful. Polymers are not just bigger molecules. They are interaction amplifiers. They respond to dispersion, polar, and hydrogen bonding forces over their entire chain. They introduce time-dependent behavior. They define the real-world success or failure of coatings. This is why Hansen Theory is far more than a compatibility chart. It is a tool to engineer polymers with solvents and additives. In the next episode, we will explore solvent blend design using Hansen parameters. We will see how engineers create robust, scalable, and predictable formulations. If you are ready to move beyond single solvent thinking and start engineering multi-component polymer systems, continue with this series. This is Hansen Theory.